One. Perfect. Hello, everyone. Today, our speaker is Chris van den Broeck, and he will tell us about probing strong gravity with gravitational waves. Please, Chris, begin your lecture.
Thank you, and thank you for the kind invitation. So yes, probing strong gravity with gravitational waves. As probably you all know, there are gravitational wave detectors active now, and they have been making detections already. These are large interferometers that look for the effect that gravitational wave has, one effect being that it sort of stretches and squeezes space as a kind of tidal wave. So there are two large interferometers in the United States. Those are the LIGO interferometers. They are 4 by 4 kilometers. Then in Italy, there's Virgo, which is 3 by 3 kilometers. Those three have been making detections already. In Japan, there's a detector that is about to join the network, let's say, 3 by 3 kilometers. In Germany, there's a smaller interferometer, 600 by 600 meters, which probably will never be a detection machine, but it was instrumental in the development of certain techniques, advanced interferometry techniques that then were implemented in the large interferometers. And there's no competition between these instruments. That would be bad. We need to collaborate and jointly analyze the data, which is what we do. And this has a number of advantages. A simple example is suppose that a signal appears somewhat weak in one detector, but then it is strong in two other detectors. Then, of course, you just want to combine that information and see what you can say about the confidence you have in the event. That's a trivial advantage. Another advantage is that if you have a global network of detectors, then you can do a kind of triangulation and figure out the position of the source, which is important for those sources of gravitational waves that also emit electromagnetic radiation, for instance, the collision of two neutron stars. If you can localize them on the sky, then you can tell the astronomers with the regular telescopes to point their telescopes there, and you will gather more information that way. And then another advantage actually is that you can disentangle the polarizations of a gravitational wave. In general relativity, there are only two, but in generic metric theories of gravity, there can be up to 6. So that already goes towards testing general relativity, which is what the talk mainly will be about. So now there's several types of sources of gravitational waves that one can envisage. An example would be not this one, but looking for a primordial gravitational wave background that is a bit like the cosmic microwave background, except in gravitational waves, of course. And these primordial backgrounds may have been generated a fraction of a second after the Big Bang. I think that would be a fantastic thing to see. But in this talk, I will focus instead on the sources we are already seeing and what we are actually already learning from them. And here's a cartoon picture of the coalescence of compact objects. Two neutron stars are two black holes. Let's say it's two black holes. Then what happens is initially the two black holes will be on very wide orbits, large separations, but they'll be orbiting some common center of gravity. And then what gravitational waves do is, first of all, they take away orbital energy, so the orbits are going to shrink. And they also take away orbital angular momentum, so the orbits are going to circularize. And by the time the frequency in gravitational waves is sufficiently high that the signal can be visible within the bandwidth of our detectors, by that time you can assume that the orbits will have circularized. And then we are in the regime of quasi-circular inspiral. And this goes on until some last stable orbit is reached, at which point the two black holes plunge towards each other and merge to form a highly excited black hole that then needs to shed its excitations and then it moves to a quiet state. Below you see the shape of the gravitational wave. So during the inspiral, you have a monotonically increasing frequency. As you can see, the tips of the waves getting closer together. Here, there is a convenient characterization of that part of the signal in terms of post-Newtonian techniques, as they are called. I will not go very deep into theoretical technicalities here, but the post-Newtonian formalism is essentially one in which quantities like the phase of a gravitational wave or the amplitude of a gravitational wave, they are expressed as a expansion in powers of v by c, where v is the characteristic velocity of the binary. Then at plunge and merger, approximate these post-Newtonian approximation break down, and here we need input from large-scale numerical simulations, and that has happened. And then finally, when you have a single black hole that undergoes what we call ring down, there you can use perturbation theory. You look at perturbations around a Kerr background, essentially. And we've been able to combine all that information, theoretical information, stitch that all of that together into a single inspiral merger ring down waveform. Now, a lot of detections have been made, 50 detections, and there's more candidates being analyzed. That is sort of what you see here on the vertical axis. You see masses in solar masses, and the horizontal axis doesn't have a meaning. But each time you see two blobs here being connected to a single blob with arrows, that sort of is indication of, okay, so we saw a merger of two black holes, and you can read off the masses. And then, yeah, so those are the black holes. Also, neutron stars, binary neutron stars are good sources for gravitational waves. Here so far, we have only seen two. Now, so mostly binary black holes, which is convenient for this kind of talk because actually a lot of fundamental physics can be probed that way. And these discoveries have been hugely important, I would say. And that is illustrated by this plot here. So what am I showing? Well, on the horizontal axis, you see the time scale of some astrophysical process like perihelion precession of Mercury, could be something else. So some time scale associated with a process. And on the vertical axis, you see the sort of a measure for the space-time curvature associated with that process. And the solar system resides in the bottom right corner. That's the most boring place you can be in this plot if you're interested in testing general relativity. The place where general relativity really counts is the top left of this plot. Strong space-time curvatures, very short timescales, meaning very dynamical processes. Until 2015, the most quote-unquote general relativistic astrophysical system that we had access to was a binary pulsar that has a period of a few hours. That is still a long time scale over which you have variability of your space-time curvature. And if you look at the space-time curvature of the binary as a whole, that is actually comparable to what it is at the surface of the sun. So the individual neutron stars, if you're standing on them, that's a different story, of course. But when it comes to the binary motion, it really is, it doesn't involve strong curvatures. Very different a very different scenario we have with the direct detection of gravitational waves. Here are two of the first batch of detections depicted here. We are in the strongly curved regime and space-time curvature changing over sub-second timescales. And if you want to test general relativity, you had better have access to the regime where it really counts, and that is exactly here. So that is the case now. And so we can look at the nature of gravity from an observational perspective, an empirical perspective now. But before I go there, it is instructive to look at something called Lovelock's theorem. And I could read this off here, but let me paraphrase. Basically, Lovelock's theorem assumes it says if you have four space-time dimensions and you want to describe gravity using a metric and nothing else, and you want the dynamical equation for that metric to involve derivatives up to second order, and you want general coordinate invariance, and you want some notion of conservation of energy momentum, then the only dynamical equation you can write down is the Einstein equation with the possible inclusion of a cosmological term. And the reason this is interesting, normally if a theorem has very many assumptions, then probably it's less interesting or something. But in this case, it is interesting because you can now think of dropping one or more of these assumptions, so that the Einstein's equations are not the only thing anymore that you can write down, and see where you get in that way. So, for instance, in string theory, one might want to go to higher dimensions than 4. So then you relax that assumption of the theorem here, or you could introduce extra fields. Other than the metric, you could introduce a scalar field or even a vector field that also helps mediate the gravitational interaction. People do this for a variety of reasons. One motivation for introducing extra fields and therefore formulating an alternative theory to generativity is the desire to describe things like dark matter or dark energy, to see if you can describe those in a dynamical way as a result of the gravitational interaction. In other words, it could be that dark matter doesn't consist of particles after all. It could be that what the effect that we attribute to dark matter, that is actually a result of our misunderstanding of how gravity works. This is possible. Then there's theories who violate diffeomorphism invariance, or put simply general coordinate invariance, and so on. So that means so as you again relax one or more of the assumptions that go into Lovelock's theorem, you get a plethora of alternative theories. It's a zoo of alternative theories. And of course, we would like to test them all using gravitational waves. But a problem is that for most alternative theories, I would say all of them, we do not have full inspiral merger ring down waveform models, gravitational waveform models of the same quality as the ones we have in generativity. And that's a problem because the way we analyze the data is essentially you have the data stream coming out of the detector, and you think there's a signal somewhere, so you try to match a waveform to the data, and it had better be, especially if you're going to do fundamental physics and try to test these things, it had better be the case that the waveform model that you try to match against the data is good. And so that's not yet the case. So there's more work to be done on the theory side then. But for this reason, with the LIGO-Virgo collaboration, what we do is we don't test these alternative theories, we test GR itself. Which is not a bad starting point, I would say. And in particular, what we do is what we call model-independent tests. What we do is we take the predicted waveform from generativity, and then at selected places in the mathematical expression for that waveform, we introduce possible deviations. We allow for possible deviations, and then we again check that new waveform model against the data and see if the deviations are there, whether nature is actually using those degrees of freedom, or whether what is in the data uses those degrees of freedom. So yeah, fundamental physics with gravitational waves. What I just mentioned is, well, one can look at the strong field dynamics of spacetime and ask whether this inspiral merger ring down process is consistent with the predictions of GR. Since most gravitational wave sources are at near cosmological distances, the gravitational waves have to propagate over large distances, and one can then think of looking for evidence for dispersion in gravitational waves. In generativity, gravitational waves in vacuum do not undergo the dispersion, but we will see examples of where it might happen in alternative theories. And then what is becoming more and more important, because points 1 and 2 have essentially already been done in some amount of detail, but what is more and more important now within the collaboration is what is the nature of compact objects? Put differently, these massive objects of tens of solar masses that we see merging all the time now, how confident are we really that these are the standard Kerr black holes of classical generativity? And then there's a number of ways you can check for possible deviations from the standard black hole paradigm sort of the Kerr black hole in generativity. And the reason why this is becoming more and more important is, well, intrinsically it is important, of course, but also our instruments are acquiring the kind of accuracy or the kind of sensitivity that is starting to allow for these tests. But I'll get to these things. So first, let me talk about the strong field dynamics of space-time. So I mentioned this inspiral merger ring down process. I also said that during the inspiral, you have a post-Newtonian description of the inspiral phase. So basically, the phase of the gravitational wave is a function of time, but you can also express it in terms of the orbital velocity, which is monotonically increasing. And if you do that, then you'll see that the phase as a function of velocity now can be expressed as an expansion in v by c. And the coefficients in that expansion in red here, they depend on the masses and also the spins of the two black holes, but in a way that is a prediction of that is predicted by general relativity, at least in this approximate sense. And then also the merger ring down regime is governed by additional parameters, beta and alpha, they're called, but I won't go into them too much. And now, like I said, you can allow for deviations in these parameters, and then see whether the signal that is in the data favors a deviation or whether it is consistent with GR. And that is what is being shown here. So what are these blobs, first of all? Well, these blobs are probability distributions. They are the probability distribution for some deviation from GR in, for instance, the post-Newtonian coefficients. So you have a probability distribution based on the data, so based on the signal that is there. If general relativity is to be correct, it had better be the case that all of these probability distributions are consistent with zero, and so far that is the case. This way we are probing extremely rich physics. My favorite post-Newtonian coefficient is the 1.5 PN coefficient here, not only because it is the most tightly constrained, but also because it is the lowest post-Newtonian order at which the dynamical self-interaction of space-time makes itself known through so-called tail effects. It is also the lowest order at which spin-orbit interactions come in, and then one order higher at 2 PN actually spin-spin interactions also enter. I should stress the importance of having results like these now, because before the direct detection of gravitational waves, humankind only had access to this leftmost panel here, nothing else. Okay, and these higher orders were totally inaccessible to us. And then what is important later on is it is possible to combine information from multiple detections so as to make a stronger statement about the accuracy of, or the validity of general relativity. And the bounds that are implied here on deviations from GR roughly will get better with 1 upon the square root of the number of detections. Okay, so that was the sort of testing the dynamics of that inspiral merger ring down process. We can also look at how gravitational waves propagate and check whether there is dispersion of gravitational waves. Again, in pure GR, gravitational waves in vacuum don't undergo dispersion, but if there is a non-zero graviton mass, then dispersion could happen. Basically, if you switch on a graviton mass, of course, what we see directly is not gravitons. We don't detect gravitons, we detect classical waves. But nevertheless, if you introduce a graviton mass, it also has implications at the classical level. In particular, for gravitational waves, it will mean that in a Fourier decomposition of the wave, the higher frequency components will travel faster than the low frequency components, and both will travel slower than the speed of light. And in any case, that is an effect that sort of is cumulative over the large distances that the wave has to travel, which means that we can very accurately make statements about whether there is dispersion or not, and put a bound on the mass of the graviton. So this is the best bound currently from gravitational waves, order 10 to the minus 23 electron volts. By the way, this is 4 orders of magnitude better than the best bound on the mass of the photon. Okay. And then, well, instead of having this dispersion relation here, you can introduce more complicated things. So P is momentum, and so you can introduce something that goes like P to some power alpha. And when you do that, the case alpha equals 0, by the way, corresponds to the mass of graviton. But if alpha is non-zero, then that corresponds to violations of local Lorentz invariance. There are various theories, models that give you various values for this coefficient alpha, this power alpha here. And then, of course, capital A tells you about the size of the violation, sort of. I won't go into these theories here, but what we did was, well, we just, looked at different values for alpha, as you can see here, alpha equals 0, half, 1, 1.5, etc. And for all of these different values, you can place an upper bound on the magnitude of A. And the reason there's two panels here is we did this separately for negative A or positive A. And once again, the accuracies with which you can measure things are fantastic. Okay, this is 10 to the minus 19, 10 to the minus 20, 10 to the minus 21 pico electron volts to some appropriate power. So these were among the first ultra high precision tests of general relativity that came out of the direct detection of gravitational waves. I should also mention we don't just look at binary black holes. We have also seen by now 2 binary neutron star inspiral mergers. And the first one in 2017 is the most famous one because it also came with, we were able actually to localize this one on the sky. And that meant that astronomers were able to look at that patch in the sky and even found the afterglow. But before that, just 1.74 seconds after the end of the gravitational wave, a gamma ray burst was seen by 2 satellites. Here's one of them in orbit around the Earth. And again, given the fact that light and gravitational waves had to travel over a huge distance, but they arrive with this difference here, which presumably only has an astrophysical origin. But nevertheless, that allowed us to sort of bracket a possible difference between the velocity of gravitational waves and the velocity of light. And so that relative difference has been constrained to about 1 part in 10 to the 15. That too was important because I mentioned certain alternative theories of gravity that were designed to explain either dark matter or dark energy in a dynamical way, rather than introducing some new field or whatever, or particle. Certain families of theories actually were predicting almost that there should be a big difference between the speed of gravitational waves and the speed of electromagnetism. And so with one beautiful measurement, a number of these theories had to be thrown away. Now, returning to black holes, so what is the nature of again, what these tens of solar mass objects that we now see merging all the time? How confident can we be that these are really the black holes of general relativity as opposed to something else? And what could that something else be? Well, there's a bunch of possibilities. Some are better motivated than others. So let me go through them. Boson stars, here the idea is that if you have a bosonic field with a self-repulsive interaction potential, then you could imagine that these bosonic fields or condensates, that they form star-sized objects. They can be quite compact, and in fact, they can be so compact that they will start resembling a black hole. Then there are dark matter stars. So imagine that dark matter is composed of particles, and in particular fermions. Then just through fermion degeneracy pressure, you can have stars that are held up by that. And those are dark matter stars. Also, depending on the mass and the mass of the particle involved and how it couples, you can have extremely compact objects that way, nearly as compact as a black hole. So again, a black hole mimicker. Gravistars are maybe less well motivated here. They're a bit contrived, actually, I have to say. So here the idea is that you have an object that has a de Sitter core, but it's being held together by a shell of ordinary matter. Wormholes, rather more speculative, then prompted by Hawking's information paradox on the string theory side. Fireballs and fuzzballs were thought of. A fuzzball is a ball consisting of strings. Again, all of these types of objects, it is not that they are necessarily so well motivated, but if you're going to look for the possibility that what we see merge is not black holes, then you need to know what to look for. And the reason why people are interested in these various exotic objects here is not necessarily that they believe they're there, or it's not because they are so strongly motivated by this or that. It is that by studying them, you will learn about certain effects that will be present if two such objects spiral towards each other and merge, and then maybe have a ring down. And if you know what generic effects even might take place when you have alternative objects to black holes, then you can look for them in a targeted way. And my expectation would be if the things we see merge are not standard Kerr black holes, then it's probably going to be something, or I would guess it would be something that is not even in the current literature yet, but it is nevertheless of great interest to look for this, of course. So what are these effects that we will be looking for? I will get through these in more detail in a minute, but anomalous effects during the inspiral. So for instance, if you have not black holes, but very compact boson stars, then as they get close to each other, they will tidally deform each other. They exert tidal effects on each other. And that has an imprint on the gravitational wave signal that is rather distinctive, actually. And so you can look for that type of effect, but there are other effects during inspiral I'll get back to. Then when the two objects have merged and you have a single object that is ringing down, you can study the ring down. So in general relativity, as we'll see, the ring down needs to be composed of modes with particular frequencies and damping times and no others. If you see different ring down frequencies from what is predicted by GR for Kerr black holes, then obviously you're not dealing with a Kerr black hole. And then finally, gravitational wave echoes, which again don't occur in general relativity, but if you have some exotic object, then it can happen that periodically bursts of gravitational waves escape from the object. But again, I will come back to these things. In fact, let's first look at anomalous effects during the inspiral that one might be looking for. So I already mentioned tidal effects. So imagine two objects. The second object is not shown here, but what I do show here is a tidal field on a body that is exerted by that other non-shown object, which to leading order, let's say, causes a quadrupole deformation in this object. And this quadrupole deformation, to the approximation used here, is proportional to the tidal field exerted by the companion object. And the proportionality here is the tidal deformability, which depends on the mass of the object being deformed, and also on what I call equation of state, EOS, its internal structure. Now, for black holes, again, to the approximation made here, this tidal deformability is identically zero. Black holes do deform each other in the end when they're almost merging, but here we're talking about the inspiral. Then boson stars or dark matter stars will have a positive tidal deformability. As they get closer to each other, they become egg-shaped, and the tips of the eggs are pointing to one another. And in the case of these strange gravastars, the objects that have the sitter core, a self-repulsive core, but it's held together by some shell of matter, there the tidal deformability is negative, actually. So as they spiral towards each other, they get deformed, but not in a way that the tips of the objects point at each other. Rather, they get deformed like this. In any case, so that is something you can look for. Now, you need to know how these tidal effects enter the gravitational waveform, of course, and they enter at very high order. I was talking about post-Newtonian order. Well, fifth post-Newtonian order is where the tidal effects enter, which is v by c to the power 10 beyond leading order. Okay, so you might say, yeah, but this is hopeless. Then this is, our detectors are going to have some limited sensitivity. We're not going to see these tidal effects, but actually that's not the case. And the reason is that the coefficient of this very high order term, the coefficient can be very large. The way these tidal deformabilities enter at that 5p order is through this combination here, which is dimensionless in geometric units. So it's the tidal deformability divided by mass to the fifth, which goes roughly like radius upon mass to the fifth. And again, that can be a large number. So in the case of neutron stars, it can be up to 1,000. And in fact, indeed, we are starting to gain insight into how deformable neutron stars are. That's already being done. Here we're talking about more exotic objects, of course, but this is just to say that, sure, the tidal deformability enters at very high post-Newtonian order, but the coefficient that comes with that can be quite large. And as a consequence, these tidal effects could be measurable for black hole mimickers such as boson stars. And that is what is illustrated here. So basically on the vertical axis, you have the accuracy in percent to which you can measure basically this combination here. And you see that for certain boson star models, what is called minimal here, details don't matter now. In a wide range, you would be able to find these, not only find these tidal effects, but measure them down to the few percent level. And obviously we're now talking not about neutron stars anymore, but about these objects of tens of solar masses that might mimic black holes. Here's another anomalous effect that you could have during inspiral. So when an object spins, then if it is made of matter, let's say, then it's going to get squished, of course, or alternatively, it's going to acquire a centrifugal bulge near the equator. And so the spin of an individual compact object in a binary also introduces a quadrupole moment. And this is what it looks like. So m is mass, chi is dimensionless spin, and kappa is a prefactor that in the case of black holes is identically 1. And then for boson stars and dark matter stars, kappa is positive. And then gravastars are always the contrarian. So for them, kappa can be negative. And you can now, just like in these tests of the post-Newtonian coefficients, you can allow for deviations from the expected value for black holes in this case. So you can, pardon me, introduce this delta kappa here. Now, for these two signals of binary black hole coalescences, these were selected because the total mass of the system was fairly low, which means that the duration of the inspiral is very long. And if you're looking for anomalous effects during the inspiral, then those are sort of signals you want to target, right? So what is shown here is a measurement of, well, delta kappa then for these two. And again, a measurement means a probability distribution based on the data. The reason there are two panels here is that on the left, it was assumed that delta kappa could be positive or negative, whereas on the right, it was restricted to be positive. Now, you might say, this is not a very accurate measurement, right? Because fine, you know, let's focus on the right here. These probability distributions, they favor 0, but nevertheless, they have this fat tail that goes to very high values, 100, value of 100 for delta kappa. So you might say, well, if delta kappa is to be compared with 1, this is a lousy measurement. But that's not the case, actually. So plausible theoretical values for kappa in the case of boson stars go up to 150. Okay, so suppose there would have been a boson star involved in one of those two inspiral signals, then what you would expect or could expect is that this distribution would look quite different, namely that it would have a bump around delta kappa of 100 maybe or so. So despite limited detector sensitivity, already we are establishing constraints on these things that are of interest. So that is inspiral. So now let's go to ring down. So like I said, the ring down regime, there you can model things as a Kerr metric with linear perturbations on it. And then you will find that in terms of the gravitational waves emitted, a ring down signal is going to be a superposition of what we call quasi-normal modes. And they look like it's a superposition of damped sinusoids, each of which comes with some characteristic frequency and a characteristic damping time. Now, that's one thing. Then separate from that, there is the no-hair conjecture, which basically says that if you have a stationary black hole that is electrically neutral, as it would be expected for astrophysical black holes, then the geometry of such a black hole is completely characterized by its mass and its spin. Now, what does that to do with ringing black holes? Stationary black holes don't emit gravitational waves, so we have no access to them. We can only see black holes that ring. But nevertheless, there is a connection with the no-hair conjecture, because if you consider linear perturbations around a Kerr background and you plug them into the linearized Einstein equations, then you will see that linearized Einstein equations enforce specific dependencies of all these ring down frequencies and damping times upon just mass and spin of the final black hole you're asymptoting to. And this sort of can be viewed as maybe an indirect test then of the no-hair conjecture, but nevertheless, it's something you can do. And this is something we are doing, therefore. So again, you can look for deviations from the expressions that are predicted by GR. What these expressions are, I'm not showing them, but they are known. Okay, so people know what they are, maybe not for all values of this LMN, but for the dominant ones. So you can take them and in your waveform models, you can introduce relative deviations, these delta omega LMN and delta tau LMN, and see whether you get consistency with 0 in your measurements. So this is a measurement from a rather recent LIGO Virgo paper, which has a whole catalog of tests of relativity, by the way, well worth reading, I think. But here's a first measurement of the consistency with the GR and Kerr black hole prediction for, in this case, the dominant ring down frequency and damping time, which are the frequency and the damping time of the 2-to-0 mode. Okay, so L equals n equals 2 and n equals 0. And the contours you see here, again, you have to have probability distributions. That is what comes out of a measurement, a probability distribution for what, in this case, a deviation parameter can have based on the data that you actually have in hand. So here you have in principle a two-dimensional probability distribution, but what is plotted here are contours that enclose 90% of the probability. And they're shown for the ring down of these 3 events. These 3 events were chosen for this type of test because they are very high mass, which means that the ring down regime is in a frequency region where our detectors have the best sensitivity. Their inspiral is very short, but here we're not focusing on inspiral, we want ring down. Okay, so these events were selected. And the most constraining event is GW 190521 here. That's this green contour, and you can see that we are constraining possible deviations in the predicted frequency to better than the 25% level, and then maybe similar in the direction of the damping time here. Again, these are not high accuracy experiments yet, but it is nevertheless amazing that they can be done now, right? And as detector sensitivities improve, and in fact new detectors are being built, I'll get to that. We can hope to get to higher and higher precision tests, which are indirect tests of the no-hair conjecture. All right, then. One can also devise a test of the area increase theorem. So here's what the idea is. Well, what does the theorem says? First of all, basically it says during a binary black hole merger, the total horizon area should not decrease. So how would you test the area theorem then with gravitational wave observations? Well, let's assume that the ingoing black holes, when they're still sufficiently far from each other, can be considered Kerr to within detector sensitivity. Now, from the inspiral signal, you can measure the masses of your 2 black holes and also the spins that they had at some reference time, because actually these spin vectors they precess and also the magnitudes can vary. But you can measure masses and spins from the inspiral signal. Now, for a Kerr black hole, the expression for the area of the horizon is simple. It is this. It goes like mass squared, and you have some dependence on spin. Well, what was the original total horizon area then? Well, you have the mass of your one object and the spin of your one object, and then for the second object, you stick these into this expression and you sum them up. That's your initial horizon area. Then for the final black hole, you have access to the ring down, right? And we have just seen that, at least in GRF for Kerr black holes, the ring down frequencies and damping times are all specific functions of the mass and the spin of the final black hole. So using those, measuring ring down frequencies and damping times, you can actually obtain the mass and the spin of the final black hole. And again, you stick those into this expression and you get the final horizon area. And then according to the theorem, so the final horizon area should not be smaller than the initial horizon area, or this relative difference here should be greater than or equal to 0. And so let's see what is the result. Well, here's the result. So here's a measurement done on, again, a gravitational wave signal that happened to be convenient for this type of test, which happened to be the very first detection of gravitational waves, actually 2 black holes in 2015. Never mind why there are 2 curves here. Let's focus on the green one, it doesn't matter much. But again, you have a probability distribution based on the data, this time a probability distribution over this delta A by A naught. And the gray region is excluded by the theorem, but we're testing the theorem. So we want to know how far this distribution goes into the green region. And with this event, you see that there is agreement at the 95% level. Again, this is not a super accurate test or something, but you have to, everything has to start somewhere, and it is certainly an interesting thing that this can be done now. And then finally, gravitational wave echoes. This is more speculative. So here you need exotic objects that have some correction near the horizon, or actually the horizon may not be there. Now, what happens in the case of ordinary black holes, when they have merged, there will be gravitational waves that go outwards towards infinity and get picked up by our detectors. But there will also be ingoing gravitational waves that normally disappear behind the horizon, never to be seen again. But if you have a black hole mimicker, let's say a boson star, then the interior structure can be quite interesting. You can have these effective potential barriers. The ingoing gravitational waves can be trapped between an inner and outer barrier. So you can view them as bouncing back and forth. And each time you have a reflection here, some amount of gravitational waves can escape towards infinity, and in the form of a burst. And these bursts will come at regular times. Now, if you have a microscopic horizon modification, or something replacing the horizon, I should say, with a characteristic length scale, little m, that in geometric units is much smaller than the mass of the object, then the time between successive echoes takes on this particularly simple form. And what is interesting here is that you see that there's only a logarithmic dependence on the characteristic size of the horizon modification. And instead a more or less linear dependence on the mass of the object here. And by the way, this p-factor little n here is simply set by the nature of the object. And yeah, if you believe in wormholes, then n is 8. For these thin shell gravastars, n is 6. Then for a particularly contrived model, namely an empty matter shell, n equals 4, and so on. But n is order 1, let's say, or order 10. One of the two is typical. But let's put in some values now. So let's take again the very first detection of gravitational waves, presumed binary black hole, 150914. Its final object, that was the result of the merger, had 65 solar masses. Let's take our horizon modification scale, little l, to be the Planck scale. Well, if you stick everything in and you make a choice for n like 4, you find that the time between successive echoes is 170 milliseconds. Now, why is that interesting? Well, first of all, this is much longer than the typical duration of the ring down, which for this mass is 3 milliseconds. So you will not, these echoes will not be drowned out by the ring down signal. They are separate in time from it. That's good. And on the other hand, delta t could also have come out to be 1 million years, and then there would be no point to look for them, right? Instead, you have this time that is convenient, that is not too long and not too short, and it is worth looking for these echoes. So here, I think I'm getting in trouble with time, so I'm going to speed up a little. So theoretical predictions for what echoes might look like, what the shape of an individual echo might be these predictions are in early stages, and moreover, it will depend rather on what type of exotic object you wish to consider. And like I mentioned, it is entirely possible that that these exotic objects or black hole mimickers exist, but it's possible that they're of a type that has not been envisaged yet, and there's nothing in literature at all. Then, and then we don't know what the shape of these echoes are. So the initial searches for echoes had to assume something about the possible shapes of echoes. And basically what these searches did was you take the ring down signal or the merger ring down signal, and you assume that the shape of the echoes will be a distorted version, let's say, of that merger ring down signal. That's one thing you can do, but by now we're more sophisticated and we are doing morphology independent searches for echoes. And the way this works is you take your data and you decompose it into what is called generalized wavelets, which is an expensive name for a succession of sine Gaussians. And they are characterized by a bunch of parameters, but basically the idea is that you have a sine Gaussian that is one thing. Then you have a next sine Gaussian at some separation delta t from the first one. It can have widened. It can have been damped by some constant factor relative to the previous sine Gaussian. There can be a phase difference and so on and so forth. Now, what I should stress is what I'm plotting here is not meant to be a template waveform for an echo signal. Rather, this is a particular basis vector in a function space that you can decompose your echo signal into, right? So, and then you have an almost morphology independent search for echoes. For the basis vectors, we do assume a morphology. You have to say something. What is your basis vector going to be? You have to make a choice, but that doesn't matter much actually. And in any case, so these generalized wavelets, you end up with an overcomplete basis actually in the relevant function space. And now you can do a largely morphology independent search for echoes. I can't go into too much detail, but basically it is possible to construct 3 hypotheses that you are going to evaluate based on the data. One is the signal hypothesis, which just means that there's a signal, an echo signal in particular in the data. The glitch hypothesis says that actually no, there weren't echoes in the data. Rather, there were instrumental glitches, temporary malfunctions that happen all the time. And if you're not careful, you're going to mistake them for an echo signal, right? So we are careful, and we evaluate that glitch hypothesis, and then there's a hypothesis that the data is just ordinary, boring noise, stationary Gaussian noise, as we say. So, but let me move on. Basically, you can calculate based on the data what is the probability for there having been an echo signal versus the probability that there would have been glitches in the instruments. And so that is what is shown here. What is depicted here is this log base factor. The base factor is just a ratio of these evidences here. And what you need to do is you need to, first of all, know how this log base factor is going to behave when there's no signal present. But there are glitches in the noise. There's noise to begin with, right? Interferometers are noisy instruments, so you need to compute what is called the background distribution for your detection statistic, which you will compare the foreground measurements with. And what are the foreground measurements? Well, once you have the background distribution, what you're going to do is you look at the various binary black hole signals that we have found, and in some stretch of time after that signal, you're going to look for echoes, and you're going to apply your methodology here, and you will arrive again at a base factor, a ratio of evidences. Now, the vertical dashed lines here are measurements of the log of the base factor for these various signals. The reason I have 2 panels here is that we make a distinction between events seen in 2 detectors and events seen in 3 detectors, because the 3rd detector, Virgo, actually has slightly different noise properties. So, but that's all, you want to make that distinction. But what you see is, and that's the bottom line for now, the log base factors for the foreground measurements are completely consistent with background. Therefore, we have no statistically significant evidence for echoes that may have been there subsequent to these events. And to drive the point home, you can, I mentioned that you basically what you do is you take a potential signal or the data actually, and you decompose it into these generalized wavelets. That means you can have a signal reconstruction if a signal is there. So what is shown in the top left panel here, the light gray is just detector noise. But in the detector noise, to do a simulation, we hid a echo signal deliberately. And then we checked whether our methodology could reconstruct it. And yes, it did so perfectly. However, all the other panels correspond to, what was reconstructed in terms of signal at times following certain presumed binary black hole mergers, and they flatline. There's nothing there to see. That doesn't mean echoes don't exist. It just means, it could mean that our instruments are not sensitive enough yet. So we need a bigger boat, and we will have bigger boats. One is LISA, the Laser Interferometer Space Antenna, which is scheduled for launch by the European Space Agency in 2034. This is again an interferometer, but an interferometer consisting of two probes in orbit around the Sun. With a distance between the probes of order 1 million kilometers, and they exchange laser beams, and therefore they form an interferometer again. Now, a rule of thumb, if you have a device that is looking for waves, then the bigger the device, the longer the wavelengths typically you will be sensitive to. And since this gravitational wave detector will be so huge, again, arms of 1 million kilometers, will be sensitive to very low frequencies between 10 to the minus 4 hertz and 1/10 of a hertz. By contrast, our current ground-based detectors are sensitive between about 20 hertz and a few kilohertz. With LISA, different types of sources will be seen. So we know that there are black holes of tens of solar masses, or we think we do because we think we see them merge all the time. But it is generally believed that in the center of almost all galaxies, there are supermassive black holes with masses between 100,000 and 10 billion solar masses. Some galaxies will host 2 such black holes, and the mergers of these supermassive binary black holes, that is what you will see with LISA. Another rule of thumb is that the more massive your system, the lower the frequency at which the merger takes place. And that is why you need a space-based large interferometer to see supermassive binary black holes merge. What I will find very interesting is to see this type of system, whereby you have a supermassive black hole, but in orbit around it is something that is much less massive, like a 10 solar mass black hole or even a neutron star. And you can get these extremely complicated orbits, which will leave a detailed imprint upon the gravitational wave signal that will be emitted. And then around the same time, we hope to have in Europe what is called Einstein Telescope, and in the United States what is called Cosmic Explorer. Einstein Telescope will be an underground observatory, a few hundred meters underground, to get rid of man-made seismic noise, basically seismic noise coming from cars, planes, trains, what have you. It'll be a triangle of 10 by 10 by 10 kilometers. And yeah, it will have certain technologies that go beyond the current state of the art. And with Einstein Telescope, you will get a factor of 10 improvement in sensitivity over the intended design sensitivity of LIGO and Virgo. And that factor of 10 is important, actually, because what does a factor of 10 improvement in sensitivity mean? It means that you could see things out to distances that are 10 times larger. And if you can see things out to distances 10 times further than currently, that means you cover the entire visible universe. And so that means merging binary black holes and neutron stars will be visible throughout the visible universe. It also means that you have access to a huge volume of space, and we will have in the order of 100,000 detections per year. And so, yeah, that is then. So let me summarize. The first direct detections of gravitational waves have enabled already fantastic tests of general relativity, strong field dynamics, propagation of gravitational waves, probing the nature of compact objects. Then I basically presented you with a list of highlights What I find the most interesting are the latter two. We are more and more moving towards looking at the nature of these compact objects. And I find it amazing that conjectures and theorems that were formulated in the 1960s and 70s by people that were then considered by other physicists, sometimes like ivory tower mathematicians or what have you, these theorems and conjectures are things that we now start to have empirical access to, and not with very high measurement accuracies, but it can only get better, and it will get better. In particular, we will have ultra high precision tests of GR and of the black hole nature, or the Kerr nature of black holes with Lisa Einstein telescope, Cosmic Explorer. And yeah, I'll stop here. Thank you for your attention.
Thank you very much for a very nice talk. And now we've got time for questions.
So maybe I ask you, you say area increase theorem. How practically you confirm this increase? What do you measure that you can state what is area of?
Yeah. So basically, an assumption is being made here, and I think that is what you're pointing to. Mm-hmm. So basically, what we measure directly are the masses and the spins of these inspiraling balls. And the reason you can measure them is that, of course, if you take some other masses and some other spins, then the shape of the gravitational wave will be different, and that shape will be a less good match against what is actually in the data. So that is what we measure directly. And then we do something that, for now, is somewhat simplistic. We just use, for the individual black holes, the Kerr formula for the area in terms of the event horizon, in this case, in terms of mass and spin. You might say, yeah, but as these things get closer and closer together, then this Kerr assumption is not going to be valid anymore. And that's true. But at this point in time, our detector sensitivities are such that that distinction is irrelevant. The measurement uncertainty is such that it doesn't matter. This approximation is good enough.
Okay, does it mean that, I'm always suspicious when people say about black hole, astrophysical type of black hole, but it means that these astrophysical black holes have something to do with mathematical conception of Hawking area increase theorem. Yeah? So it's not so bad that we are in different worlds.
Yeah.
Good. So, but can you imagine, say, you used to work in mathematical theory too. Can you imagine this process of merging really as a mathematical fact, or it is too hard to imagine? What happens? These are
So certain tools. Yeah, so certain tools have been developed. On the analytical side, there is a notion of dynamical horizons, which are basically stackings of outermost marginally trapped surfaces. But a lot of information is also coming from large-scale numerical simulations, where you basically use the ADM formalism. You formulate initial conditions on some spatial slice. You discretize the Einstein equations, and you evolve them in a discrete way as well. These numerical simulations have really come to fruition. And they are becoming of amazing accuracy, actually. In fact, the people who, I'm not involved in such things, but the people who work on this have developed a variety of techniques to place upper bounds on the kind of errors they are making due to the necessarily discrete nature of whatever you put on a computer, right? And that is getting very interesting and useful to make measurements.
Thank you.
Further questions, please?
I have a question. Okay. Okay. In one of the initial slides, you show the slide where was measurement of curvature of the space-time. How it is in fact it is done? In which way?
Oh no. So what I'm doing here is to give an indication of sort of I want to have some number that is going to tell me how strongly is spacetime curved, right? So what is the measure that I use here? Well, I have some object like the binary pulsar here. I take the mass and I divide by a length scale cubed, the square root of that. That is going to be my measure for how strongly curved something is. So what this plot is meant to be is you can put here the Kretschmann scalar, by the way, if you want. But the main thrust of this plot is not mathematical rigor. It is to demonstrate the enormous difference in terms of what is a curvature scale, or in terms of time scales, the enormous difference between what we see here versus what happens in the solar system, which is here.
But in fact, it is calculated in some sense. It's
in a very
direct.
simple
It's
way.
not a direct measurement. I understand.
No, of course not. But this plot is meant to be illustrative. Okay, so it's meant to convey the many orders of magnitude difference in something to do with curvature and time in the case of gravitational wave observations versus, for instance, the solar system, or for that matter, that binary pulsar.
Thank you.
Next questions, please.
I would have a question.
Okay.
Sorry.
Okay, I just sign up. That at the end, please don't disconnect. At some point, I will also ask a question.
Right. So I have just a small question concerning this one event when the people managed to observe the afterglow of the merger.
Right. Yeah.
So I mean, there's somehow this delay between the merger and the afterglow observed.
Yes.
And could you perhaps tell us a bit more? What is the reason for this delay? I mean, because apparently the gravitational waves and the electromagnetic waves are supposed to both travel at the speed of light, so they should arrive simultaneously.
Yeah, absolutely. Yes, exactly. Good question. So it's equivalent to asking, so with this time delay here between the end of the gravitational wave and the arrival of the gamma ray burst, how do I bracket my velocities? What is the reasoning that I'm applying here? And the reasoning is as follows. Let me consider two extreme cases. One extreme case is when the gamma rays will have been emitted at the same time as the gravitational waves, but you see the gamma rays arriving with a 1.74 second lag. In that scenario, light would have gone slightly slower than the speed of light. Let me go for the other extreme scenario. That is one in which there is first the gravitational wave, and then 10 seconds later, the gamma rays get emitted. But again, upon arrival, the difference is only 1.74 seconds. So in that scenario, the light will have gone faster than the gravitational waves. And so using those two extremes and considering the distance from source to observer, that is how I get the lower bound and the upper bound for the relative difference in velocities. And then to complete the story, in the second scenario where I assume that the gamma rays were emitted 10 seconds after the gravitational waves. Where does the 10 seconds come from? Well, there is no plausible astrophysical model that would give you gamma radiation more than 10 seconds after the merger. So there are some astrophysical assumptions that go into these bounds here.
Yeah, but I mean, okay, so I mean, we're taking into account both possibilities, that either the light signal or the gravitational wave signal goes faster. But are there any, I don't know, plausible theories why one should go faster than the other?
Yeah, I didn't go into detail, but there are alternative theories of gravity that I forget the name now. I'm not a theorist anymore, haven't been for a long time, but there are alternative theories of gravity. I'll be able to give it to you afterwards in an email if you want, where they were designed to try and explain either dark energy or dark matter in a dynamical way as a side effect of gravity rather than having to invoke a new type of particle in the case of dark matter. And some of these theories did predict a large difference between gravitational wave velocity and the speed of light. And whatever those theories are, they're not alive anymore.
I see. Thank you.
Okay, Jerzy, please.
I have question concerning those mathematical subtleties which we have in mathematical theories describing gravitational radiation. So since you have this mathematical physics background, maybe you are also sensitive on this kind of issues. So for example, what about the positive cosmological constant? We know that mathematically it makes big difference in the framework of describing gravitational waves. Do you see any influence on that of that mathematical difference in global structure of space-time on possible observations?
I don't see, I cannot think of a way, but that doesn't mean that doesn't exist. But I cannot currently think of a way how you would probe this empirically with foreseeable gravitational wave detectors, let's say. Again, that might be my limited vision or something, but yeah, for now I don't see a way.
And the second question, similar mathematical effect, is this ambiguity in definition of angular momentum. We know that this angular momentum depends on super translations on Scry. However, some mathematical relativists define angular momentum in a different way, such that it is invariant. And what about the observational point of view? Can you somehow tell mathematicians which definition is correct, which is wrong?
No, I wouldn't presume to do so, but I think so. Basically, when it comes to these sort of things that then lead to observations, of course, I usually take recourse to, okay, what is done in numerical relativity, because whatever they do, they will have to end up with something that is practical. The practical result is what is the prediction for gravitational wave emission. It has to be practical, it has to be feasible. And so what do we see them do? Well, we see them they have to come up again with initial conditions of some three-dimensional slice. They will have a boundary, by the way. They cannot assume a spatial slice that goes to infinity because computers can't handle that. So, pardon me. So basically, they have to make certain assumptions, and however, within the assumptions, yes, you have a boundary in this case. Nevertheless, what you do is on your initial spatial slice, you essentially solve the constraints that are necessary there, admittedly in a numerical way, and then you evolve, and then whatever comes out of that is hopefully going to be close to the truth, but it has its limitations, of course. Yes.
But I suppose that they use, like you write here, Kerr solutions. Yeah, say 2 Kerr black holes, something similar to this. So if these solutions are axially symmetric and stationary, then angular momentum is well defined. Yeah? So I assume that the initial conditions with 2 Kerr black holes, if they are somehow separated first, they both are well defined.
Yeah, reasonably well defined, and certainly sufficiently well defined given the measurement accuracy.
Yes, but this problem which is pointed out, for instance, in Abay Ashtekar's papers, in your former supervisor's papers, is that the DVL is in this kick-off velocity. So if there is zero velocity of the total system after the coalescence, then we can naively translate our calculations in observations. On the other hand, if this velocity is not zero, then this spin of the resulting black hole has to be, the relation between the spin and the mathematical calculation is more complex. That there is some contribution from super momenta. So I'm wondering how
I have proposal for you. Next week we have free spot for you. You can tell us.
Well, I would like to learn about this from from Chris, because, well, you know, mathematics is non-fiction. I wonder what people who observe.
Yeah.
So, but the bottom line is you observe this kick of velocity, right? That the resulting black hole has different total velocity than the velocity of the initial system.
So you mean a kick in the sense of after the merger,
Yes.
the resulting black hole has a velocity even up to hundreds of kilometers. It shoots off with hundreds of kilometers per second, right? Because of an asymmetry or anisotropy in the way gravitational waves get emitted at the very point of merger. Yeah. I have to admit, I have not kept up with, you know, with mathematical literature on this. I'm very much on the observational side, but I'm willing to learn. That is what I will say. If there is something that useful to us that we can test or that we can look at, then I will certainly always be interested in that.
So maybe ask you. So what is your say part in these considerations?
Well, data analysis, right? So that is the daily work. The data comes in. So there's okay. Let me explain a bit the structure of the LIGO-Virgo collaboration then. So there are people who do the searches, so they look for signals in the first place, and then once a signal has been detected, then I take over, and together with other colleagues, of course, meaning then we're going to scrutinize that signal in a lot more detail. So the detection process doesn't require very good waveform models, and that's a good thing, because otherwise it would be computationally too expensive for us to find gravitational waves in the data. But after that, once a signal has been identified, then you can throw everything at it, right? Again, subject to computational constraints. I wish I could give I could give a second talk, but you know, with more technical details of what that actually means. What that actually means also involves things that another type of mathematician or theoretical physicist might be interested in, namely how do you efficiently explore functions in the case of binary black holes, 16-dimensional parameter spaces, so not physical space, but parameter space. And there's all sorts of techniques that do that then. But then, you know, what are the scientific results? Well, my main interests are what I just explained. So trying to find deviations either from GR or from the Kerr nature of black holes. Secondly, and somewhat related actually, the interior structure of neutron stars. I mentioned these tidal deformabilities that we can measure now actually. Which will give us a lot of insight into the internal structure of neutron stars. So I work closely with theoretical astrophysicists who are interested in neutron stars in particular. And then there's also cosmology, which means standard sirens. So until recently, cosmological parameters like the relative densities of radiation, matter, dark energy, and so on, and the Hubble constant could be measured with standard candles. If you see binary neutron stars, or you could even use binary black holes, then you have a new way of measuring distances. I didn't even talk about that at all, but an amazing thing, or very interesting thing about gravitational waves is that from the signal itself, if it is observed in multiple detectors, you can actually extract the distance to the source without reference to anything else. So these gravitational wave signals from in particular binary inspirals have given us a new distance measurement method.
Can I ask you the question regarding that actually? You said that in the GR, there is no dispersion, but there is attenuation or energy dissipation possible. And usually people say there is no. Could you comment a little bit on this assumption? And exactly this brings this distance question then. How accurate the statement is that there is no energy dissipation at all?
What I'm assuming is that in GR, in expressions like this, for the dispersion ratio of a graviton, there's no second term. That's a local statement. I think that's a well-defined statement, isn't it?
No, what I'm saying is that you determine the distance from the amplitude of the gravitational wave. And in principle,
right, yeah.
there can be an energy dissipation, and your amplitude is not only geometrically, so to say, defined, but you had some energy losses. So my question is, how good this assumption is that there is no, on the cosmological distances, there are no energy losses at all?
Let me ask you, so what do you envisage the energy loss to come from? Is it the fact that we don't live in a perfect Friedmann-Robertson-Walker universe? Is that what you mean? Or do you mean interaction with matter?
I mean interaction with matter.
Oh yeah, so those effects can be shown to be so tiny compared to, well, what would be the effect of a graviton mass had it been larger than this number here. By comparison, those are totally negligible effects.
And there are no even exotic scenario when it is becoming relevant. You say that it can be very safely ignored.
Yeah, at least this late in the evolution of the universe, I don't know of any even exotic scenarios that would give you such strong interaction with matter that we wouldn't have seen it before, actually, or maybe that would violate or that would probably constitute a large violation of general relativity, I would think.
Because, you know, we might reach a very high Z. So I'm talking not necessarily about the present observations, but in future,
absolutely,
when you start to really go to the, you know, very different conditions. And I just wonder how, you know, how solid this assumption is. But okay, you say I should not worry.
Yeah, even in that case, I don't think you should worry. One could entertain ideas like, suppose there is, suppose that within our nominal horizon distance, suppose there is somewhere a large deviation from Friedmann-Robertson-Walker in terms of the background metric that you would be allowed to assume. Maybe, yeah, but I don't think there's strong reasons to assume that this is the case.
Okay, do we have more questions? I can't hear any, so let me have a question, okay? So what's the situation with the detection of primordial gravitational waves?
Yeah, good question. Yeah, it's gonna take a while. Is the answer, and the reason is as follows. So we know that we know now more or less what is the rate of something else, but I'll connect that to the primordial gravitational waves. We know now what is the rate of binary black hole mergers in at least the part of the universe we can observe. The rate in, you know, how many mergers per year per cubic gigaparsec, let's say. Given that rate, you can actually predict that very soon we will see what is called a stochastic background, which looks like a primordial background, but it isn't. A stochastic background of all the binary black hole signals from the entire visible universe. Most of those cannot be picked out individually. Our detectors aren't accurate enough, but we will be able to detect sort of the pileup of all these signals coming again from edge of the visible universe, and that will cause a gravitational wave background. And that's also interesting, of course. But unfortunately, that binary black hole background, together with possible other astrophysical backgrounds, like for instance, pulsars in the Milky Way, it could be that it's going to be a long time before we see the gravitational wave from a particular pulsar that we can identify. You know, but what we might start seeing reasonably soon as well, is the sort of the confusion noise caused by all of the pulsars in the Milky Way galaxy. And these so-called astrophysical gravitational wave backgrounds are going to mask with current detectors whatever primordial gravitational wave background might be in there as well. Or at least that is the most likely scenario. The exception would be that, by miracle, the primordial background is so strong that our sensitivity is, the bottom of our sensitivity is only just above it, and with the next upgrade of detectors, all of a sudden it's there. Okay, that's possible, but that would mean that the primordial background is stronger than this astrophysical background. It's a possibility, but we would have to be extraordinarily lucky. So does that mean that in the frequency range of ground-based detectors, at least, we will never see a primordial background? No, that's not what that means, because in the case of Einstein telescope, it will be able to see, again, binary black holes in the entire visible universe, but it will be able to identify them individually. So Einstein telescope will not have a pileup of signals that we can only see as some sort of background. No, it will pick off the individual signals. If you're able to do that, you can subtract them from the data. And then you will be able to look for a truly primordial gravitational wave background.
Thank you. Thank you very much indeed for your absolutely nice talk, and we I think finished the formal part of our meeting, but after that we can have an informal